Okay, thank you everyone for coming here. Very warm, and I may add humid welcome to those who are physically here. We are just before our monsoon season, which is a lovely season also to be here, lovely rains. So it's a great pleasure to have all of you, and in particular our keynote speaker, Professor Milind Tambe of Harvard University. There are a lot of good things to say about Milind, but before I come to that, the topic of today's talk is, he does many things. So today he is talking about AI for social impact, results from deployments for public health and conservation. So this is basically the AI for good. Of course, these days AI has a lot of things going on around it. There's AI problems and there's AI for good. So today we will hear this side. But AI against bad is the other side, which also we hope to hear from more from Milind in future talks and others. It's a very important area. To introduce Milind, by the way, this is a Sigmetrics conference. Your first keynote talk is on AI. The chair of the session is a database person. So clearly Sigmetrics is very big on diversity, going beyond the usual definitions of diversity. So thank you for having us non-Sigmetrics people. Milind is also a Sigmetrics person. But okay, so Milind is the Gordon McKay Professor of Computer Science and Director of the Center for Research in Computation and Society at Harvard University. Concurrently, he is also Principal Scientist and Director of AI for Social Good at Google Research. He has many, many awards. Can't list all of them, but just to mention a few, he is a recipient of the HKI John McCarthy Award, the AMAS ACM Autonomous Agents Research Award, the AAAI Robert C. Engelmore Memorial Lecture Award. He's a fellow of AAAI and ACM, a recipient of the Informs Wagner Prize for Excellence in Operations Research, and RIS Prize for Military Operations Research Society, so he spans many areas. For his work on AI and public safety, he has received the Columbus Fellowship Foundation Homeland Security Award and commendations and certificates of appreciation from US Coast Guard, Federal Air Marshal Service, Airport Police at City of LA. Quite an impressive list of people who have benefited from his work, which we will hear more about today. It's also worth mentioning that Milind is local. He's from Mumbai. He's from South Mumbai. If you're a Mumbai local, you know there's South Mumbai and then there is North Mumbai. We are the northern side here. So he's come all the way from South via US, of course. So thank you for coming here, Milind. Oh, I should also mention, he started the football match, at AMAS. And if you want to introduce this tradition at Sigmetrics, he will help you organize it in future.
Okay, I will not do that again. Well, thank you very much for inviting me, and really appreciate. It's a great honor to be here. Yes, I grew up in Mumbai, close to that place, just a couple blocks over there. So that's good that you have that picture up there. All right, so For the past 15 years, my research team and I have focused on advancing AI and multi-agent systems for social impact, focusing on topics of public health, conservation, and public safety and security, with the key challenge of how to optimize our limited intervention resources. Let me put this watch here so that I know what time it is. So let me just jump right into the lessons we have learned. First, achieving social impact and AI innovation go hand in hand. So with respect to public health, we have large populations to serve, but limited number of public health resources. Concrete example is work we have done with youth experiencing homelessness in Los Angeles. We're harnessing the social networks of these youth. We're able to show that our influence maximization algorithms are far more effective in reducing HIV risk behaviors compared to traditional approaches. However, this work required innovation in the area of social network and bandit algorithms. With respect to conservation, we have large conservation areas to protect limited number of ranger resources. Concrete example is work we've done in Uganda and Cambodia. We're harnessing past poaching data. We are able to predict where poachers set traps or snares, and for the past several years have been able to remove thousands, if not tens of thousands of these traps. This work required innovation in the area of what we call green security games, which combines machine learning and game theory. With respect to public safety and security, we've contributed a new model called Stackelberg security games and contributed new algorithms that have been in use by security agencies in the United States, such as the US Coast Guard, the Federal Air Marshals, LA Airport Police, and others. Today's talk will focus on public health and conservation. At first glance, these may seem like very different areas from each other, but they're tied together by this underlying system of multi-agent systems research. Lesson 2 is that all of this work requires partnerships with communities, with nonprofits and governments. So here's the logos of some of the nonprofits that we've worked with. Our ultimate goal is to empower these communities to use AI tools and avoid being gatekeepers to AI technology for social impact. A third lesson is that when we are working on AI for social impact, we go beyond just improving, making methodological contributions, just improving algorithms. It's important, but really here we need to look at the entire data to deployment pipeline. We start our work by immersing ourselves in the domain, trying to understand what kind of data are available to the nonprofit, what kind of problems they face. Following that, a predictive model makes predictions on which of the cases faced by a nonprofit are high risk versus low risk. We cannot intervene on all of the high risk cases. Therefore, a prescriptive intervention algorithm tells us which cases to actually intervene on. And finally, field testing and deployment is crucial, not only because we want to test our models in the field, but because this is AI for social impact. Social impact itself is a key objective. If you don't have social impact, it is not AI for social impact. So in the rest of this presentation, I'm going to outline for you 4 projects with this diversity in these projects. We just discussed diversity. The first is restless bandits in maternal and child care. This is based mostly in Mumbai. The second is social networks and HIV prevention. This is based in Los Angeles. Third is COVID-19 testing. This is probably helpful for everybody worldwide. And finally, poaching prevention using game theory and so forth. That's in Uganda and Cambodia. So it's hopefully you can see that it's a diverse set of projects. I'll cover papers for the past 5 years from NeurIPS and ICHCA and AAA and so forth. Most of the times I'll focus on real world results. There are lots of simulations and so forth that are available in our papers. And I'll highlight the role of the key PhD student or postdoc by putting up their picture in the top right-hand corner of the slide on which their work is shown. So let's start with the first topic here of maternal and child care. So the United Nations Sustainable Development Target is that by 2030, maternal mortality ratio should be below 70 per 100,000 live births. That is, mothers dying during pregnancy and childbirth and so forth should be below 70. So where are we today? If we look at Western Europe, very low, United States rising, but still much lower than the UN target. In India, it's dropping, but it's still way above 100. And that's where we start today with maternal and child care. As you know, you may know, a woman dies in childbirth in India every 15 minutes. 4 out of 10 children are too thin or short. 2 children under age 5 die every minute. And so we are very fortunate to be working with a nonprofit called Arman, which works with 26 million beneficiaries in India, mothers, and is operating in 19 states in India. We are very inspired by the founder of Arman, Dr. Aparna Hegde, who says pregnancy is not a disease, childhood is not an ailment, dying due to a natural life event is not acceptable. So we were all inspired, but the first task is exactly what can we do with AI and how? And that's actually a very crucial question, trying to figure out exactly where can we make a contribution. So after a lot of discussion, we arrived at one program that they run called mMitra. And the problem is one of program adherence. mMitra is a weekly 2-minute automated message to a new or expecting mother. It's 141 messages that go out in a local language, Marathi, Gujarati, etc. And it will be something like, you're 3 months into your pregnancy, you should use this health supplement, or your child is 3 months old, get them vaccinated, etc. And Arman has shown with randomized control trials that mothers who listen to these messages derive significant benefits for their own health and health of their babies. And 2 million mothers are enrolled so far in mMitra program. So where do we come in? Unfortunately, 30 to 40% of the mothers who enroll become low listeners over time. They just drop out of the message, of the whole program. Now, to understand why, we were very grateful that Arman took us around to the sites where they serve these beneficiaries. So we went to the hospitals where they enroll the beneficiaries and the localities where these beneficiaries live. And basically, these are families that are living way, way under the World Bank determined international poverty line, which is like less than $2 a day per person. And so you can imagine the stresses that are on these families and why they may drop out of this program, mMitra. But Arman has this service call center from where they can make calls to these beneficiaries to encourage them to stay in the program. So the question for us is, how can we optimize these limited resources that Arman has, because they can't call everybody. So I'll give you an example. They have a large number of beneficiaries enrolled, say 100,000, and they have to choose 2,000 to call every week so that you encourage mothers and maximize the number of health messages that are listened to. So here's an example. We have a health worker. She has 5 mothers under her care. 4 have not listened to the health message, which is shown in red. 1 has, which is shown in green. And now she has to decide, she can call 2. Which 2 mothers should she call? Supposing she calls the first 2, this was a good choice. They turned green. In fact, one other mother turned green. And so now this was a good choice. Now she has to decide next week which 2 mothers to call. So she says, okay, I'm going to go for the 2 red. But this turns out to be a bad choice because not only do these 2 mothers don't turn green, but the 2 who are green also turn red. The point here is that a call may not change a beneficiary state. This is a service call going out to encourage them to listen, may not change the beneficiary state. But beneficiaries could change state on their own. And yet you have to prioritize 2,000 beneficiaries per week. And the question is, how do we do that? We model this problem as a restless bandit. We're trying to pull K out of N arms per week. So here, each arm in a restless bandit, for those of you may need a refresher, each arm is a Markov decision problem. Each arm essentially models a mother. So mother might be in a bad state, she has not listened to a voice message, or a good state, she has. And you have 2 actions available. One, we can intervene on the mother by doing a service call, or not. And there's a transition probability, which is based on, if we don't call the mother, the transition probability of going from bad state to good state is low. If there is a service call, the probability rises. Now, of course, in reality, we have 100,000 of these mothers, have these 100,000 MDPs, and we are trying to choose 2,000 out of them. So the problem is p-space hard. It's not easy to come up with a fast solution. We rely on what's called a Whittle index. So we compute this Whittle index for each arm. Essentially, it's computing a benefit of intervention on each arm, then rank them and pick the top K. Formally, a Whittle index is essentially the minimum subsidy to be given to the passive action such that the benefit of the passive and active action become equal. We have developed an algorithm back in 2016 that we use to compute the Whittle index and then choose the top K. The challenge here, of course, is that normally this restless bandit literature has assumed that the model parameters are given. When we have no model parameters, where do we draw them from? So here we have past beneficiary data, mothers who have engaged with Arman in the past. So we have features like age, income, education level, etc. An engagement sequence. This mother was not engaged. There was a service call, she engaged, etc. So based on this past data, we cluster it and then map a mother with a particular feature, age, income, etc., to a transition probability. So that in the future, when a new mother comes in, we know, given her features, what are her transition probabilities. And then we compute the Whittle index and choose the top K mothers. There's a lot that happens here. I'm going to skip some of the details, but basically this clustering is useful because we have very limited data, and it also speeds up our Whittle index computation because we are not computing a Whittle index of each mother. We are only computing a Whittle index per cluster. So having done all this, then we launched a study with 23,000 mothers. This is the first large-scale application of restless multi-bandage for public health as far as we know. We divided these 23,000 mothers into 3 groups. A restless banded group, which had 7,667 mothers. There's a round-robin group and a current standard of care group. So in each group, we pulled 225 arms, that is called 225 mothers per week. In the RMAP group, the restless banded group, the mothers were decided based on who had the top Whittle index. In the round-robin group, we call the first 225, then the next 225, etc. The current standard of care is that there is no call that goes out from the call center. So we are now going to look at what is the benefit of doing these methods of service calls. So how many more health messages, the voice messages that mothers were not listening to, how many more of those are these mothers listening to because of our service calls? So here's weeks on the x-axis, and how many more messages were listened to by the mothers over the current standard of care method. And what we see here is that with the round-robin group, we have hardly any difference that gets made over the current standard of care. So calling people round-robin doesn't help, but the restless banded group is able to pick the right mothers to call, and as a result, 600 more health messages have been listened to by these mothers. We looked at statistical significance. The restless bandit versus the current standard of care is significant, but round-robin versus current standard of care is not. And so overall, what we find here is that it is important to optimize these service calls because just calling people in round-robin fashion, etc., doesn't help. And this AI algorithm leads to about 30% reduction in drop-off rates over the current standard of care method. So done. So we have now transitioning this software over to Arman. There's a very nice video made by a very talented team. If you want to go take a look, AI for Social Good in partnership with Arman. And we are very grateful for Dr. Aparna Hegde saying that we're able to reach out to more women each week and get them back into the fold and save lives because of AI. And a mother who got a service call and as a result started listening to the advice and taking good care of her baby. So our goal now is to complete this transition, and by 2023, be in a position where we are assisting 1 million beneficiaries for Arman. So this is Arman, this is the local NGO. Government of India runs another program called Kilkari, which is similar to this Mitra program, but their scale is much bigger. They have 25 million beneficiaries across the country enrolled. And this 5.2 crore is like 52 million audio messages that go out. And so that's our next goal, to work with this Kilkari program and be of assistance to them. Of course, there's lots and lots of further research to be done. First thing, why did service calls help? So we surveyed 500 service call receivers and asked them, did service calls help your listenership? And yes, 60%, no, 40%. But why? So among those 60%, majority said the reason they started listening is because they got more motivated, they got more information about the Mitra program. We also, having collected all this data, could build a nice simulation now to compare other benchmarks. So for example, why did we need a whole Whittle index? Could we do something very greedy? And it turns out that the greedy algorithm, when we did simulations, doesn't do as well as the Whittle index algorithm. But there are lots and lots of additional challenges. One of them is called decision-focused learning. So I talked about this data to deployment pipeline. We start with immersion, getting problems, data, learning features to transition probability. So we work very hard to make sure that we are as accurate as possible in the learning aspect. And then, find the stop K using the Whittle index. And we try to be as good as possible at that optimization. However, this is a two-stage process where we first maximize learning accuracy and then optimize to maximize decision quality. However, maximizing learning accuracy doesn't align with maximizing decision quality. So I'll give you a quick example here. So this is an illustrative example. On the x-axis is some feature. On the y-axis, we are looking at transition probabilities. The blue dots are all low-risk mothers. They're in majority. The red dots are the high-risk mothers. Those are the ones we actually want to do something with. Now, if you do two-stage and you are forced to use a linear regressor, then you can see that to the left of the orange line are all the blue, to the right are all the red, and the linear regressor is going to learn this green line, making for high learning accuracy is going to be able to predict accurately the transition probabilities of mothers, but it's going to miss the high-risk mothers, which are in minority, who we are actually interested in. Decision-focused learning modifies the loss function to directly maximize decision quality rather than learning accuracy. And what this means is it learns a linear regressor as shown, whereby we have a lower learning accuracy because this green line shown at the bottom clearly is not learning anything particularly useful, but from terms of decision quality, it picks the mothers of high risk. And so this is decision-focused learning that we've been focused on, and we have applied this to Arman in simulations and shown that indeed two-stage leads to high predictive accuracy as shown in the left plot. So you can have high accuracy with respect to predicting transition probabilities, but low solution quality compared to decision-focused learning, which is bad at accuracy of transition probabilities, but good at actual final policy performance. Another area of interest is tuberculosis prevention. So TB is also a big challenge in India. 500,000 Indians die every year. I mean, it's a global challenge. 3 million are infected every year. And TB treatment requires that a patient take this medicine for 6 months. I get tired if I'm given a course for like a week. So 6 months is a very long time, and there's a lot of side effects. So patients drop off, which is not nice for them because they don't get well, and then we also have drug-resistant bacteria. So to prevent that, again, there's a call center method by which a health worker can call patients to remind them to take their medicine. The question is which patients to call. Here, the question is that the call center worker actually doesn't know what was the state of the patient. Did they take their medicine or not? So when she calls, that's when she realizes, oh, two of these when she calls the first three, the two of these took their medicine last night and the third one did not. And so now she has to decide based on this information who to call tomorrow. So this seems very similar to the Arman problem that I just showed, except there's partial observability. And so our newspaper looked at restless bandits with partial observability. And the basic idea is when there's no observation, you just update beliefs. Generally, you have a probability with which adherence is taking place. And when there's no observation, no call, you update that belief. When there is a call, uncertainty collapses. When you call a patient and the patient says, I took my medicine last night, now uncertainty collapses, you know the state of the patient. Or the patient says, I didn't take my medicine, you know the state of the patient. This is what we've called collapsing bandits because immediately the uncertainty collapses. And we can exploit this to not only provide performance guarantees, but also develop a fast algorithm. So here blue is our algorithm, which performs better than the best baseline without giving up much in solution quality. So there's a lot to be done here in terms of online learning, robust bandits, restless, risk-aware restless bandits and so forth. So, and this area certainly we feel very excited by given the social impact that is possible. So if some of you are interested, I encourage you to work on this area. All right. So let me now shift to the second topic, which is HIV prevention. So this was when I was in Los Angeles, right outside my university, USC at the time. There was a homeless encampment. And so, just drive by, not paying attention to these homeless encampments, which is not nice. So eventually I said, okay, we have to figure out what can we do. And so I teamed up with our School of Social Work. And so one of the challenges they pointed out is that there's 6,000 youth who sleep on the streets of Los Angeles every night. but the rates of HIV in this population are 10 times the rates of the normal house population. So homeless shelters then try to figure out how to spread information about HIV prevention. They can't reach all the 6,000 youth. So they'll call some peer leaders, educate them about HIV prevention, expect these peer leaders to talk to their friends to talk to their friends, and information to spread in the social network in this fashion. Now, these are real face-to-face interactions. These are not happening over Facebook, etc. So for people who may not be familiar with influence maximization, the general idea is you're given a social network here. Each number is a youth, each edge is a friendship edge, and we have to choose key peer leaders so as to maximize the expected number of influence nodes, those whose behavior have changed, reducing HIV risk behaviors. This is a picture from our collaborators educating these youth in real life. So how does information spread? We assume the independent cascade model. So you educate youth C about HIV prevention, adjacent youth D gets informed with a probability of 0.4, and if D is informed, they're going to inform their neighbor C with a probability of 0.4, and information is going to cascade in this fashion. So unfortunately, despite the 2 decades of work in influence maximization, applying this in the context of our homeless youth domain was challenging. And this is one of the lessons, again, from AI for social impact. The lack of data and uncertainty is a key feature of AI for social impact. You can imagine people saying, after looking at these challenges, that, this is not a problem I want to work on because you're not giving me the right data. But that is where you get your PhD. So there's uncertainty in propagation probability over edges. I said 0.4, but we don't know exactly it's 0.4 or what. Secondly, these are youth under difficult circumstances. You call them and say, we are going to teach you about HIV prevention. One of them may choose to run away from LA. One of them may have other difficulties. They may send someone else. So there's a lot of no-shows, and now we have to build a dynamic policies to bring in other youth. And finally, the social network itself, which is assumed to be an input, is not available. All we have is we can do limited queries to sample the social network and still find the right kinds of peer leaders. So I'm going to sketch some ways how we solve these problems. The first is this uncertainty, right? I said, instead of 0.4, we don't know what is this probability. So we can sample it from some distribution. And furthermore, we can say even the mean of this distribution is not known, so it lies within some interval. And now we have this problem of robust influence maximization. On the one hand, so we're going to solve it by casting it as a zero-sum game against nature. On the one hand, we have this algorithm that is going to choose peer leaders, and nature is trying to choose parameter settings to cause our algorithm to perform as worse as possible. So we cast this problem as a max-min problem. We are trying to maximize, nature is trying to minimize our performance. And the performance here is the outcome of our particular choice of peer leaders to the optimal possible had we known nature's choices in advance. In our paper at AMAS, we have details about the mixed strategies and pure strategy and so forth. If you're interested here, I'm just going to sketch for you how we actually solve the game. So if you imagine 400 nodes in a network and 40 youth, that's 400 choose 40. That's a very big number for policies for the influencer. Nature is trying to choose parameter settings from a continuous interval. That's also a very large set of strategies. So representing this game in memory itself is difficult, let alone trying to solve it. So we solve this problem by initializing this game with a small number of strategies on both sides and use this double oracle approach. So then influencer's oracle gives its best response, nature's oracle gives its best response. We grow the game and iterate in this fashion until convergence, and often with a small number of iterations we converge with approximation guarantees. So this is the way we arrive at robust influence maximization. The second question is, you have a homeless shelter, you have some number of youth, you don't know their social network. One idea is send our social work colleagues, sit there for a week, try to figure out who's friends with whom, etc. This is unworkable. They're not going to do that. And if you want to take this program to other homeless shelters, it's just not going to work like that. So what can we do? So the idea is if we can sample 15% of the nodes by having our social work colleagues do a simple query such as, who are your top 5 friends? And just list that. And if we can do that for 15% of the nodes in the population, and then select K peer leader nodes to spread influence such that the performance is similar to the optimal possible. Had we known the entire social network in advance, that's what we want. And so we've developed this algorithm that samples nodes randomly and estimates sizes of the communities they belong to, and then chooses seeds from the largest K communities. We can provide some guarantees, I'm going to now skip into the experiment we ran. It was actually published in AAAI 21 in its full details. So here, change is our algorithm. It has network sampling, it has robust multi-step policy, it has peer leader selection, so everything I mentioned. And we did a study with 750 homeless youth experiencing homelessness in Los Angeles. This was work done with Professor Eric Rice in the School of Social Work. So 250 were in the change arm, 250 with degree centrality. This is the traditional approach. Bring in the most popular youth. This is what the homeless shelters had been using. In a control group where there is no influence maximization being practiced. And now we want to know at the end of 1 month and at the end of 3 months, was there an actual reduction in HIV risk behaviors? So again, as far as we know, this is the first large-scale application of influence maximization for public health. And we worked closely with 3 homeless youth shelters, My Friend's Place, Los Angeles LGBT Center, and Safe Place for Youth. And again, there's 250 youth in each of our 3 arms, and we're seeing at the end of 1 month what happened with respect to HIV risk behaviors. And what we see is that with change, there's more than 30% reduction in condomless anal sex, which is one of the HIV risk behaviors. But with degree centrality and control, there is no reduction in this HIV risk behavior at the end of 1 month. At the end of 3 months, degree centrality begins to catch up, but still not as good. And the fact that change can make this reduction happen faster is important because this is a HIV risk behavior and this is a community where youth come and go. And therefore having these reductions happen faster is important. We also looked at other behaviors like reduction in condomless vaginal sex. And again, we can see that the reduction caused by change is much better. There's statistical significance results in a AAAI 21 paper and paper in the Journal of AIDS. And some things that our collaborator said, I don't know if this will come through. Oh, no. Okay, let me just move on. She was the head of Safe Place for Youth, saying some nice things about the collaboration. There's lots of interesting challenges. One is fair influence maximization, how to ensure that all the different communities, there's no disparity in influence spread across the different communities. And also with reinforcement learning, we can get performance comparable to change, but with a very little runtime. I'm going to now change over to COVID-19, an agent-based simulation model. And I'll highlight in particular some of the work that, this is work that we did starting in after obviously all of us were shut down due to COVID. But I wanted to highlight one paper that appeared in Science Advances because this is the one that gets referenced in popular media repeatedly. So this was led by Professor Michael Mina in the Harvard Chan School of Public Health, where he approached us right at the beginning of the pandemic saying, can we do some modeling related to testing? So at that time and now, still now, we have these PCR tests, which are gold standard, which detect low viral concentration, but the cost is high, and it takes a day to get results back. And rapid tests, which many of you may have done, requires high viral concentrations, but the cost is low, and you get results back instantaneously, 15 minutes or so. So question is, if you're at Harvard and you want to test all of the students, what method should you use? Should you make everybody go through PCR and then isolate those who are positive, or is rapid test sufficient? So that was the main question that he asked us. Can we model this? So we built a model, and here's what we found. So on the y-axis is number of infections, blue is the PCR, and orange is rapid tests. So if we do these tests for all of the students and get results back instantaneously, and then isolate people who are positive, then indeed rapid tests are worse. You can see infections are rising with rapid tests compared to PCR. So yeah, go with PCR. However, in reality, there's a 1-day delay in getting results back with PCR. Just that 1-day delay implies that all of the benefits of the PCR are lost. You have a 1-day delay in isolating positive individuals, and that's enough to negate its benefit. Furthermore, because of the cost, if you can only do these tests every 5 days, the PCR, instead of every 3 days, as with rapid tests, again, all of the advantage of this PCR test is lost. So rapid turnaround time and frequency is more critical than sensitivity for COVID-19 surveillance. This paper got a lot of attention from New York Times and Washington Post and so on and so forth. We were thrilled one day to get up in the morning and find Dr. Fauci discussing our paper. That was interesting. And now, given all the work that Michael Mina has, and all the credit to him for advocating for rapid tests, we now have rapid tests available in the US for families for free. And so thanks to Michael for spearheading this effort. Okay, so the final 10 minutes or so, I'm going to talk about a different topic related to wildlife conservation. So across the globe, there are wonderful national parks and terrific wildlife. This is from Queen Elizabeth National Park. I was in Uganda a few years ago, and these are my photos from there. But there's threats to the wildlife, snares or traps that get placed to maim and kill wildlife by the thousands. And now there are hundreds of rangers for thousands of square kilometers of this park trying to look for these traps. You can imagine how difficult it is for a single ranger here trying to look for this trap, trying to patrol, figure out where are these traps. So if we can help them, that's great. So we can imagine dividing up this park in a 1 kilometer by 1 kilometer grid square, and then trying to predict where are these traps. So that's what we did. We have 14 years of data from Uganda. And so even ranger patrol frequency for each 1 kilometer by 1 kilometer grid square, animal density, distance to rivers, roads, and villages, etc. And you're trying to predict what's the probability of finding a snare per 1 square kilometer grid. Now, I'm going to skip over the modeling details and come to the first field test we ran. So here, this is in Queen Elizabeth. This was in the fall of 2016. We had to choose. So this was the test. They were saying, okay, don't tell us to go back to where we already found snares, because we already know this, that's where the snares are. Tell us to go to new areas which we haven't patrolled before, and tell us where to go. So we came up with these green areas, which they hadn't patrolled before. You can see they don't overlap with the red dots where they had found snares. And we said, if you patrol these for 1 month, you're going to find snares, traps that you hadn't found there before. So the rangers started patrolling. Every day they would send a message back. Initially there was nothing. We were getting disappointed. I mean, it's a good thing. But then unfortunately they said that they found a poached elephant with its tusks cut off. So we were too late to save this elephant, but at least the machine learning system was pointing us in the right direction. Then came good news that a whole elephant snare roll was found and removed. Then antelope snares were found and removed. This work just happened, this 1 month test just happened to be a month before the AMA's conference deadline. So what that had meant was if snares were found, we were able to write a paper. If not, there was no paper. So fortunately, we were able to write the paper. And I was pretty pessimistic that we were going to find snares. So I promised the students that I'll buy you a free drink every time a snare is found. And after these 10 antelope snares, they were like, okay, no more free drinks for us. Then came a much longer test where we looked at 3 national parks: Queen Elizabeth, Murchison Falls, and Sri Pak Wildlife Sanctuary in Cambodia, 2 in Uganda and 1 in Cambodia. We selected 24 areas in each which were infrequently patrolled. Some we predicted high risk, more snares would be found. Some we predicted low risk, less snares would be found. And the point here is that otherwise, people, you may say, you go to any national park, find an area where it's not been patrolled before, and you're going to find snares. So we want to make sure that our system is actually predicting, getting it right in terms of where to patrol. So we send rangers out for 6 months to look at these areas. And where we predicted high risk, more snares. Where we predicted low risk, less snares. And in fact, in Sri Pak Wildlife Sanctuary, the number of snare captures from 2018, when our system called PAWS was not used, to 2019, jumped 5-fold. And these are pictures of the traps that have been found because of PAWS. In March 2021 alone, 1,000 snares were found because of this PAWS. So today, PAWS has gone global. Our software is integrated into the SMART platform. SMART is this collaboration of World Wildlife Fund, Wildlife Conservation Society, and others. There's 13 wildlife organizations, and they have one software which is used by rangers globally to track their patrols and so forth. So we have integrated PAWS into SMART. What this means is now rangers are able to download our software worldwide and start using it. And it's really exciting to see messages coming from different parts of the world trying to show us how our system may be of some use. So some of the interesting collaborations. We're going to Belize in August, but Zambia, Vietnam, and so forth. So there's lots of interesting collaborations moving forward. I'm going to very quickly go over some of the game theory related to this and then conclude. So far we've talked just about prediction, but you can imagine that, we have to also think about what to tell the rangers to patrol. So for example, in this 1 kilometer by 1 kilometer grid square, if we find this red dot, which is a high risk area, and orange dot, medium risk area, and we say to rangers, always go to the high risk area, the poachers will move to the orange area. So we don't want that. So we can cast the problem as a game. And here it's a Stackelberg game where essentially the poachers get to see where the rangers are patrolling, but all they know is that the rangers go to the red area 60% of the time, go to the orange area 40% of the time, but what they'll do tomorrow remains unpredictable. And these kinds of games where the rangers commit are called Stackelberg games, and that's what we've been working on. But the adversary here, unlike our work with the public safety organizations, are not fully rational strategic adversary, but these boundedly rational poacher models where we learn from past poaching data. Again, because there's uncertainty in the poacher model, we can run this as a max-min problem. In the interest of time, I'm going to skip over some of these details and we can ask questions. Another area of work has been working with a nonprofit called Air Shepherd, which flies drones in South Africa and Kruger National Park, trying to look for poachers. And you can see from infrared, this is very difficult to know if there's a human being in this picture or not, because there's also ground heat. So my student Liz Bondi, as part of her thesis, developed a system called SPOT to automatically detect poachers and animals from this infrared. And the interesting part there is now we can do optimal deceptive signaling to scare away poachers. So basically, you can imagine that the drone is flying overhead. It knows the probability of a ranger showing up is 0.3, probability ranger not showing up is 0.7. Poachers know that, rangers know that, the drone knows that. But the drone knows something additional. The drone knows whether the ranger is actually there or not, which the poacher doesn't know. So you can use that to deceptively signal sometimes when the ranger is there and sometimes when the ranger is not there by turning on their light late at night and flying towards the poachers. And so with this deceptive kind of signaling, we can achieve more protection of wildlife. There's a challenge of data scarce park, because now you want to patrol and detect illegal activity and collect data, but also to stop animals being poached simultaneously. And so this is exploration and exploitation. So this works for domains for parks where there's very limited data. So I'm going to end here and end by outlining some lessons that we've learned in AI for social impact. First, achieving social impact and AI innovation goes hand in hand. Second, partnerships with nonprofits, governments, and local communities is crucial for AI for social impact. Third, we don't want to be engaged with helicopter science in AI for social impact with communities. Fly in, take their data, publish a paper, run away. We want to be there consistently throughout and work with these nonprofits and governments and make sure that we actually deliver good results. It's important that in AI for social impact, we look at the entire data to deployment pipeline and not just focus on methodological improvements. And fortunately now more and more conferences are recognizing that this entire pipeline, making contributions, is important, and it's not just methodological innovations that are intellectually interesting, but also field experiments are interesting and so forth. It's important to step out of the lab and into the field, and to embrace interdisciplinary research with social work or with conservation. And finally, this lack of data I mentioned earlier, this is the norm, a feature, should be part of a project strategy. So I've had students who will say, well, I can't work on this project, there's no data. But actually that is where you get the PhD. So really that is the problem, that there is no data and you still have to figure out, like in the case of this social network where there was no network, you still had to do influence maximization. For students, just in case you're interested, interdisciplinary AI for social impact work implies less papers, but impact matters. And you'll see from the results of those who have been on the job market and so forth. You have to respect domain experts because they may have a different language and you still have to respect them. take courses in experiment design, impact evaluation, courses in another discipline like public health. And problem selection, knowledge acquisition, all of this takes time. It needs patience, but it's worth it. Refer to bullet number 1. Okay, so with that, I'm going to end my presentation, and I'm very happy to take your questions. And that's my Twitter handle in case you want to keep abreast of our group's research papers. Thank you.
What we'll do is we'll alternate local questions and questions for those online. So we'll start with local. Use the microphone.
Hi, Milind. Fantastic work. Really good. 2 quick questions. One on your talk and one sort of looking beyond. With regard to any of these things, like the interventions with the women and so on, is there a notion of optimality? Like, can you say after the fact that, yes, you made an improvement, but you could have done better? Like, that's one question. The other question is that this is like going beyond social good, or actually it's not social good. One domain where your techniques could really be quite interesting is in winning elections, right? Who should, in winning elections, for example, like, the politicians would, pay for knowing who to call so that, they can. So I'm just curious whether you have thought about that or whether you think it's applicable.
So we have been very excited by many applications of these restless bandits, but we've generally stuck to different areas of public health, tuberculosis prevention. There's also other kinds of adherence problems and so on, maybe for conservation, but we haven't looked at elections and so on and so forth. But yeah, I mean, if people want to look at it, certainly very, very interesting. That's not where we are going. With respect to the first question, it's really very interesting. We were just discussing earlier before my talk that we are trying to predict the behaviors of these mothers, and there's all kinds of complications going on. So there's a training set of past mothers, and now you're saying, okay, can we predict these behaviors? And so that's where a lot of the challenges lie. So if you think about optimality, the question is, what does it even mean? So we've been looking at this decision-focused learning approach as a way of trying to say, this is the maximum you can squeeze out of this data set. Because if you knew the transition probabilities, yes, there is a clear cut, you can say this is the optimal. And under conditions of indexability, we can prove this Whittle index policy is optimal. But when the transition probabilities themselves are uncertain, it's not exactly clear what optimality is. So that's where we have been gravitating towards this decision-focused approach to try and say this is where we want. Thank you.
Thank you for the wonderful talk. I had a question about how you choose your problems. So all of the problems that you presented had some kind of algorithmic contributions, and it seems like in many social good problems that may not be the case. So I'd love to hear a little bit more about your process for choosing problems.
Excellent question. First of all, congratulations on winning the Rising Star Awards. That's an amazing accomplishment. This is indeed a very difficult problem of trying to select the right kind of problem. I can tell you that we've gone to wildlife conservation organizations in the Sundarbans and say, well, we can do AI. The minister is very interested. We want to do AI and all of that. And then you go talk to the rangers and they say, sir, we just need better shoes. We don't need AI. And so indeed, in some cases, AI is just not the right solution. But it's a big dialogue. It requires a lot of effort. We have some criteria. Actually, these are not necessarily my criteria, but Wadhwani AI, which is, there's a Raghu Dharmaraju there who had these 7 questions, which I expanded. And so these are questions like, when you meet with an organization for the problem that they propose, is there data? Would AI make a difference? Would they be able to pilot it? Would they be able to scale it? And for us as researchers, I add the question, is there an AI research problem or a straightforward, application of known techniques? But they have like a list of 7 questions. I guess I only remembered 4 or 5 here. So those are the questions we ask, plus the question of research for any organization that we meet. I should point out, in case you're interested, and for anybody here in North America, we are running a matchmaking service. So we've run it in 2020, we've run it in 2021, and there's one ongoing in 2022. So this is run from Google. So basically you apply as a faculty member, And there's a nonprofit, there's nonprofits will apply. So last time for 2021, like 150 nonprofits applied and 150 faculty members applied. And then we run speed dating. So each faculty member meets with 3 nonprofits, each nonprofit meets with 3 faculty members. Whoever matches, they write a proposal and we fund them for a pilot. And if the pilot is successful, then there's a lot bigger funding. So if you're interested, the matchmaking service this year is focused on Americas. With NGOs in South America. And so that's one way in which you can interface with nonprofits and find problems to work with. So hopefully that gives you some kind of an answer.
Thanks a lot. Yes.
Can you tell us a little bit about the challenges that you've faced in working with the stakeholders? Because usually they have some set ways of doing things. Getting an outsider to come and tell them perhaps what to do might be something that is a challenge. So how do you engage with them and how do you overcome the challenge?
Excellent question. And I guess I have faced students or postdocs who will have a first meeting with a nonprofit and say, they didn't give me a research problem to work on. And it's like, okay, but you gotta have patience, you gotta meet with them. And they have, there's, like you said, set ways of doing things. A concrete example is when we were working with the Los Angeles Sheriff's Department. They had their schedulers for counterterrorism exercises where they, schedule people. And we had our game theoretic mechanism. And at first, it was, you go into their room and there's a lot of tension and they're like, we don't need these AI people, they don't know anything, this is our domain, et cetera, et cetera. But our students, went on patrols with them, kind of understood what they were trying to do. And when the Sheriff's Department realized that really they are trying to help us and they're humble and these are not like ivory tower academicians coming in and trying to impose their will, but really trying to assist and find the pain points in which they could help. That turned out to be a huge win. In the end, when there was a human versus machine competition. So at the end of the day, after the whole day's competition, they announced the winner, and the winner was our algorithm compared to the human. So I was expecting the human schedulers to be upset, but they actually went and hugged the postdoc who had done that, because by then there was enough of a relationship built up and an understanding of trust and so forth. So I would say that for us, the key here is beginning to end, partnership, partnership, partnership. It's partnership in problem definition, data collection, algorithm development, testing, evaluation. And with that kind of an approach, we have found that even if, it's the Boston Coast Guard, for example, we're trying to tell them, here's how you should patrol your boats, and, this is the better way of patrolling. I mean, they're going to say, who's this person? They don't, this is my port, I have been patrolling here for so many years. How can he tell me what's an optimal patrol? But that's the beginning. That's the way the meeting starts. So they're all sitting like this. And then over time, as this partnership kind of starts to develop, we see that they start coming in with ideas for how to improve our algorithm and help us move things forward. So I guess the other idea is patience. So I've been in meetings with a domain expert and OR colleague of mine who are in conversation about substance abuse prevention in youth experiencing homelessness. The person, the OR person wants to say, give me an objective function. And the domain expert is saying, we've been talking for so long, the objective is crystal clear, get the kids off of drugs. What more do you want? But the OR person wanted like a sum over I, xi, something. And it just takes a lot of time to kind of get used to each other's language.
So Milind, this question is particularly related to the last application you mentioned regarding poaching related AI work. I'm just wondering what impact the dissemination of this work has on its efficacy. I assume this is not necessarily the case with your earlier work, but I'm just wondering whether that's the case here.
So you're saying the poachers would kind of figure this out, and then they start deceiving the AI. algorithm and so forth. Fortunately, they're not reading our papers, and fortunately, they're not looking at things. However, in Cambodia, we were going to go there in 2019 in spring. And just before that, our algorithm was deployed. Apparently, as a result, as you saw, the number of snares captures went up. No, I mean, the poachers apparently got upset. They had a firefight with the rangers. One of the rangers was shot. They had to be in the hospital. And so there is clearly a reaction from the other side. They're not going to keep quiet. It's a multi-billion-dollar industry of wildlife poaching and smuggling. So there is going to be a reaction. I mean, it's a very interesting and open. We're not there yet in some ways, but we will get there because the money is just too much. And so we have to kind of figure out in this cat and mouse game what our next steps would be.
So I have a question on your intervention problem where you called up people and so on. So typically in that you model what the other side is behaving, but there is also an aspect of when the people who are intervening, when they see failures, they also sort of slacken off or lose interest and so on. So there's potentially a modeling aspect there also. So was that ever considered, or is that an issue?
No, agreed.
Experience?
No, I agree. We haven't gone there yet in terms of, but there is, for example, workload. So you can imagine that if one of the workers, just because of the way we are selecting arms, gets a lot of phone calls to make and another doesn't, that's a fairness challenge that comes up. So that's something we have looked at. But in terms of the emotional challenges, and so I have, obviously colleagues who work a lot with emotions and modeling emotions and so forth, but very interesting question and very interesting topic to think about in terms of future work.
Hi. I'm sure that the methods that you've proposed work really well in practice. But many of these solutions, like data-driven methods, machine learning, deep learning, these are more of black box models. And have you faced any apprehensions from, say, public health experts who would probably want more of white box solutions? Or maybe if you have any thoughts on how the area of explainable AI can be explored, particularly in scenarios, high-stake scenarios like public health?
Right now, I think that's a great question. We haven't exactly faced this big problem where they say, provide us an explainable solution, otherwise we will not use this. I think, as I said, this partnership from the beginning to end has perhaps allowed us to build up that trust where it wasn't necessary for us to deliver a solution where, okay, why is this patient being selected, or why this beneficiary and not that beneficiary? They get the general gist of the model, and that has been sufficient. However, the interaction, so in one of the lessons is that if you give them some new software, it's complicated interaction, you have to do this, then that, and all of that. That turned out not to be as useful. So as long as the interaction that they have with AI software is simple, like query 5 people, ask this youth, who are your top 5 friends, and write them down and feed it into the algorithm. That is doable. If we say find a random walk through the graph and every time do this and that turns out to be more difficult. This is not to say that explainable AI is not important or anything like that. It's just that we haven't faced this problem at that level. Where we have faced this problem, the problem has been so basic that it's not clear. So for example, we were working with these TB workers here in Mumbai, and they are tasked with and they're very proud of the work they do with making sure that people adhere to the taking their TB medicine and so forth. So I was trying to explain, we can predict in advance that this patient is going to drop out of treatment. And so the person was saying, I don't believe it. You just cannot predict. And so it sort of went on for a while. Okay, so how can you explain prediction to this TB worker? So I said, you can predict how much Virat Kohli will score in the next match. That kind of got him to think. But that's kind of I think for AI systems to get there, maybe a little complicated.
Yeah, thanks. A quick follow-up. In cases, say for example, if you want to expand the situation that you were looking at with women to say across the country, perhaps in India, there the stakes are very high because you don't want to even have any risk in terms of even a person or two people dying, even say across the country, because of any error, any noise in the data. So how sure do you want to be, or are you expected to be when you actually want to scale this to scenarios that are affecting common people at large?
So certainly where direct death and so forth is involved, we want to be really, really careful. And everything is, IRB certified, ethics committee approved, everything, et cetera. But the problems we have worked with so far are like improve listenership as opposed to this kind of a life or death question. And it might be that, my colleague Hima Lakkaraju and others work a lot on explainable AI, and more power to them, great work. It's just that in our experience, that has not been an obstacle.
Got it, thank you.
We have an online question. Please go ahead and unmute.
Thank you for the very interesting talk. I had a question about the idea of having field works when you're doing modeling, and I was wondering whether you had any lesson learned by interacting and going on the field to understand what were the real concerns and how the model should be shaped.
Yes, absolutely. Repeatedly, we've run into a situation where a model developed in the lab just doesn't work in the field because some very basic assumptions are just completely wrong. Concrete example is, we were doing patrolling, recommending patrols for rangers in Uganda. And that's flat ground, and they were saying, great, patrols work. Then we started working with Panthera in Malaysia. And, we were in LA, we were giving them patrol directions, and they were saying, these patrol directions just don't work. And so we were saying, what are you talking about? The shortest distance between 2 points in Malaysia is not a straight line, come on. So then they said, come here. So we flew to Malaysia. We patrolled with the rangers for a day, and suddenly, shortest distance between 2 points there is not a straight line because you got to walk along riverbeds, along ridge lines to conserve energy. And so this is an example of where going into the field, suddenly sort of people and the student there were saying, oh, there's a highway in this forest. It just runs on riverbeds and ridge lines and so on and so forth. And so if I can just model that highway, then I can get good patrolling routes. And so this sort of insight, I believe, sitting in the lab, you just can't get. And this has happened repeatedly. You can write really, really nice theorems sitting in the lab. It just doesn't work like that in the field. So and for anybody interested in this topic, I encourage them go meet with people in the field. You will learn a lot.
Once again, a question related to stakeholders. Where was the tuberculosis work done?
Here in Mumbai. And I should point out that it was not deployed. It remained as a paper. We got the data, we made predictions, there's papers, but it wasn't actually field deployed yet.
So both tuberculosis and AIDS are issues in India for which the public health system has put in place district level surveillance as well as counseling and so on. I'm sure you're aware of that as well. Have you interacted with the public health agencies, and can you tell something about the challenges you have faced?
Yes, so we worked a lot with the 99 dot system, which collected data in Mumbai, and that's our first paper on using that data to make predictions. And then we were working a lot with the chief TB officer of Mumbai, the health commissioner, and so basically it seemed like we were making a lot of progress pre-COVID, but it required that I be here in person, and things were not working on phone calls and so forth. And once COVID struck, basically it broke the back of our collaboration. There's also some political dimensions, which I can talk to you in person separately. But there was, change in governments here in Mumbai also. And anyway, so there's a lot that happened. And so we were able to make some progress, but we could do more had there not been COVID. And we were able to be here in person. So that's been an obstacle for us. HIV prevention in India, we haven't looked at as much that work. I wanted to intentionally make sure that there was a project I got here and described here, which was not in India or in a developing country context, because I wanted to be sure that people understand that AI for social impact doesn't mean that people in Western universities write papers about problems in the developing world. There's, global South right there in our backyards that we need to be aware of as well.
We have time for last one or two questions.
Hi. So regarding your work on the poaching detection, so especially in forest areas, having where there is a canopy of trees, it is difficult. But in mainly open fields, satellite images can be useful, and also rangers use cameras to detect animals. So where images from and video analysis from such sources were also used?
So, these are, so basically, for example, with drones and things like that, it's very difficult for some of these parks to afford unless the costs come down significantly. And so they are, just hiring more people is cheaper than buying a drone and maintaining a drone, for example. There are parks which have camera traps and so forth, and they do, they do a great job. And there are people who work with camera traps, but many of the parks that we work with just don't seem to have that kind of money to have all of that equipment. And so we end up having to work with rangers who are patrolling on foot. Certainly, if we have tried to explore the use of drones and so forth, and but I think practically speaking, what seems to happen is many of these parks just don't have that money.
And another important application can be in the human-animal conflict, which has been very prominent and also shown in movies recently. So, can you predict which villages, which areas animal is more prone to go to a human habitat area because of lack of food or?
Yes, we have a paper at IAI 2022 looking at human-wildlife conflict around the Tadoba forest. And so we need satellite imagery there and past conflict data. And then based on that, we make predictions on which villages are at high risk in terms of human-wildlife conflict. Here we have looked at human-carnivore conflict, which, because of tiger overpopulation and so forth, there's more of that. But it's a very, very risky area. We were talking earlier about life and death. Well, that is definitely life and death, because if you get that wrong and now somebody goes in the forest because this is a safe area and a tiger attacks and somebody dies, that's a real high risk problem. So we've just made the initial work, just published the initial work, but to deploy it or anything like that will require immense amounts of careful calibration, work with partners, trying to understand what could actually work, because we certainly don't want the AI system to lead people to have a false sense of safety, and then the tiger attacks or something like that.
Thank you.
Thank you very much. I think we are out of time for questions, but I would just like to ask Dr. Tambe one last question. I think you've covered a tremendous amount of ground on how to optimize certain things at the lower level. If you take this one level up, can you use some of these to tell policymakers what are the right interventions that are higher?
Yes, that's a great question. That's a great question. We have talked to policymakers at the top, for example, for the Coast Guard, what equipment should you invest in or things like that. But in terms of actual impact that we could measure and so forth, we found these to be, this is where we are. But I agree. I mean, being able to talk to Niti Aayog, for example, and say, here's what can be done in terms of investments or, the Coast Guard or what have you. I mean, that certainly would be, it's possible, it's interesting. We just haven't quite done that yet.
And thanks for a wonderful talk.
Thank you.
I think it's really inspiring for our grad students. I think it's given us a lot of insight for students on what problems to address, how to address them, and perhaps the next talk will be on how to work around program committees and get your papers accepted. So I think there's a lot to learn. Thank you very much for a fantastic talk.
Thank you for inviting me. Thank you.